Section 7.6, the inverse of a matrix. Definition of the inverse of a matrix. Let A be a matrix, and let I of n be the n by n identity matrix. Remember, an identity matrix has to be square, has ones on the diagonal, 0 everywhere else. If there exists a matrix which is written as A to the negative first, such that A times A to the negative 1, which is not really read as that. That's the symbol, what the symbol looks like. It's read as A inverse, as you can see down here at the bottom. A to the negative 1 is called the inverse of A. The symbol A to the negative 1 is read as A inverse. If you can take a matrix A, multiply it times A inverse, and you get out the identity matrix, and you can take A inverse and multiply it by A. Remember, multiplication of matrices is not necessarily commutative. In this case, it will be, but it is not always. If you can multiply them in both directions and get the identity matrix out, you know that the two matrices are inverses of one another. Only square matrices can have an inverse. If a square matrix has an inverse, it is said to be invertible. If it does not have an inverse, it is said to be singular. So if a matrix, square matrix, has an inverse, then it is said to be invertible. If it does not have an inverse, it is called a singular matrix. Show that B is the inverse of A if A is equal to that and B is equal to that. To verify that two matrices are inverses, in this case matrix A and matrix B, I need to show that A times B equals the identity matrix and B times A equals the identity matrix. In this case, we have a 2 by 2 matrix times a 2 by 2 matrix. So we definitely know we can multiply them together, and we're going to get out a 2 by 2 matrix. A times B, start with row 1, column 1. Negative 1 plus 2 is 1. Row 1, column 2, 2 plus minus 2 is 0. Row 2, back to column 1, negative 1 plus 1 is 0. And row 2, column 2, 2 minus 1 is 1. So we see we do get the identity matrix in that direction. Now we need to show it in the other direction. So now we're going matrix B times matrix A. So now we're row 1 in matrix B, column 1 in matrix A. We get negative 1 plus 2. Row 1, column 2, we get 2 minus 2 is 0. Row 2, column 1, negative 1 plus 1 is 0. And finally, row 2, column 2, 2 minus 1 is 1. Since A times B and B times A gives us the identity matrix, we know that matrix A and B are inverses. So that last example shows us how we verify that two matrices are inverses. What if we're just given a matrix and we're asked to find the inverse? Well, this is the process you follow. Let A be a square matrix of order n. Remember, an inverse can only exist if it is a square matrix. So it has to be a square matrix we begin with. What we're going to do is we're going to write the matrix that consists of the given matrix A, which we are looking to find the inverse of, on the left, and the identity matrix I on the right to obtain this augmented matrix where we have matrix A on the right side of our augmented matrix, its corresponding identity matrix on the right side. Step 2. This is going to be very much similar to what we did in Gauss-Jordan elimination. If possible, row reduce A to the identity matrix using elementary row operations on the entire matrix A augmented with I. The result will be the matrix I, because you're going to change that left side to the identity matrix, and what you are going to be left with then on the right side is your inverse matrix. If it is not possible to do that, then you know that A is not invertible. You're working with a singular matrix. Step 3, remember you can always check your work at the end to make sure that the multiplication in both directions gives you the identity matrix. So finding the inverse here of this matrix. Start with the original, 1, 4, -1, -3. We augment that with its corresponding identity matrix. Now we're going to use our row operations, the same exact thing that we did when we used Gauss-Jordan elimination to solve systems. We need a 1 in row 1, column 1. That's already been done. We need zeros now in the rest of that column. How are we going to get a 0 down here? Well, add row 1 to row 2. 1 minus 1 is 0. 4 minus 3 is 1. 1 plus 0 is 1. And 0 plus 1 is 1. Row 1 remains unchanged. 1, 4, 1, 0. Next, we need a 1 in row 2, column 2. That's already been done. Zeros in the rest of that column. So I need to get a 0 up here. I need to multiply row 2 by -4 and add it to row 1. When I do that, I get 0 plus 1, -4 plus 4, -4 plus 1, -4 plus 0. Bottom row, 0, 1, 1, 1. Now on the left side here, we can see that we have the identity matrix, which means then this right side represents our inverse matrix. So our inverse matrix here of this original one up here is the 2 by 2 matrix given by -3, -4, 1, 1. Those two matrices are inverses of one another. Okay, use a calculator to find the inverse of the matrix if it exists. So let's go to our calculator. Start with matrix A here. We can see that matrix A is a 3 by 3 matrix, so we're going to go into our matrix menu. Edit matrix A. We want to make that a 3 by 3 matrix and enter it in. 1, 2, -2, 1, -1, 0, 0, -1, 4. Exit out of that menu. Go back in. Select matrix A. So matrix A, we want to find the inverse of it. So hit the x to the -1. Hit enter. There's our inverse matrix. We do not want decimals, so I can go math, change to fraction, and there is our inverse matrix. So column 1, 2/5, 2/5, 1/10. Column 2, 3/5, -2/5, -1/10. Cursor over here. Column 3, 1/5, 1/5, 3/10. Letter B. Go back in, edit your matrix. We want a 3 by 3 matrix. Enter that one in. 1, 0, -2, 4, 0, 0, -2, 0, and 3. Exit out. Go back in. Pull up matrix A. We want to know the inverse of A, so hit x to the -1. Hit enter. We get an error message. If you read the error message, it says it's a singular matrix. What does it mean when it's a singular matrix? It means that it does not have an inverse.